Hello, I think we can start now. Hello everybody, we are going to start with the session. Today we are going to virtually visit the Nanoscience Center in University of Cambridge. Today is with us Harry Beeson, that is a scientist working there. He will be telling us a lot of things about his daily work and about the microscopes, what they do in nanoscience, what is nanoscience and these kind of things. We will see butterfly wings, a lot of things, a lot of animals. Also, remember that this is just an example about how you can communicate with a scientist, how you can virtually visit an important center that is located in Cambridge, in United Kingdom, and that you could not go otherwise. So this is just an example for this module 5 of the STEM MOOC. So Harry, you can share your desktop now and start your presentation. Just remember also that you can make your questions through the chat tool, and that I will be the one moderating the session, so I will be interrupting Harry and making the questions.
Okay, Enrique, so can you see that?
Yes.
And you can hear me okay?
Yes.
Okay, brilliant. Yeah, okay, so I'll start then. If you want to ask questions, you can do it through the chat, and then Enrique can ask me as we go. Okay, so yeah, thanks Enrique. As you said, my name is Harry. I'm a PhD student here at the University of Cambridge in the Department of Physics, and a lot of the work I do is here at the Nanoscience Center, which you can see on the screen at the moment. One of the pieces of equipment that is most heavily used here is the scanning electron microscope, or SEM, and that's what we're going to be focusing on today. So I'll start by explaining sort of what the SEM is, how it works, and then we'll move on to the sort of work that we use it for and what we use it to image. Okay, but first of all, we talk about, well, why nano? Why are we going to the nano scale? And some of the work that we do here is based on sort of fundamental science, but also a lot of the work we do is looking at more sort of technological applications, sort of addressing real-world problems. And one of the common themes are sort of energy-based challenges. So that might be the conversion of energy, for example, of sunlight into electrical energy in a solar panel, or the storage of energy in a battery. Things like this, and often what we're looking at is how efficient are these devices at doing what we want them to do, and obviously trying to improve the efficiency is sort of the research aim. There are different approaches that you can take to try and address these problems. So you could go for a completely new technology. An example of that might be, for example, nuclear fusion, which we haven't achieved yet, and people are working hard to try and make it possible. Alternatively, you could take existing technologies, such as I said, solar cells or batteries, whatever, and just try and sort of synthesize new materials to incorporate into these existing technologies to try and make them work better. You might think of that as a sort of a chemistry or materials approach. Obviously, what we use here is more of the sort of nano approach, where we're taking existing technologies and existing materials, but trying to structure them on a nanoscale, so a very small scale, in order to try and improve the technologies. So how does this actually work? Well, if you take your device and it's doing whatever you want it to do, you have the functional material in there, so the material that is actually performing the process driving the technology. Often, however, the processes that you're interested in are actually only happening at the surface of that functional material. And sort of the active material then is just a few nanometers into the volume of that functional material. So, for example, you could be looking at chemical reactions happening at the surface, or perhaps charges coming in and out at the surface. And obviously, you can see from this diagram straight away that the surface area to volume ratio is very important. It tells you how much of your device is actually sort of usefully involved in the process that's driving the technology. And what we want to do, therefore, is sort of maximize that ratio so that the the material is almost all surface, and there's very little bulk material in the middle that's not really being used. And that's why we come to nanostructuring. You can see the surface area will scale as sort of r squared, whereas the volume goes as r cubed, and hence as you shrink r, the radius or the sort of feature size of the material you're looking at, you essentially make the material all surface, and that can drastically improve the efficiency of the device. So that's the sort of aim behind nanostructuring in technologies. We're trying to make these processes more efficient. So if we're going to go about trying to make nanostructures to try and improve these technologies, we definitely need a way that we can image them. Now, we can't do this with optical microscopes because the wavelength of light is sort of visible light is around 500 nanometers roughly, and the sort of scale that we're looking at is under 100 nanometers or even under 10 nanometers. So the wavelength of light is just too long. You can't actually resolve the features that we're looking at. So instead of using light or photons, we use electrons, which have a far shorter wavelength, and hence this is the electron microscope. As I say, scanning electron microscope. There are different sorts of electron microscopes, but what we're going to be looking at today is the scanning electron microscope. So here's the photo of the one that we have in the center. On the right, you can see the computers that we obviously use to control the machine. The microscope itself is housed in that sort of white box on the left. The microscope is run under vacuum, and so that's why the casing is there, quite strong. And then on the left, that grey cylinder is used for detecting X-rays. So if we actually look inside to see what is going on, as I said, the idea behind the electron microscope is to use electrons rather than light to do the imaging. So at the top of the device, we have an electron gun, which is essentially a piece of metal that we heat to very high temperature. It's normally tungsten because of the high melting point, and that sort of essentially boils off electrons, which we then use for the imaging. So once the electrons are emitted from the electron gun, we focus them into a beam. Because the electrons are charged particles which are moving, they're affected by magnetic fields. So you can use magnets to form the lenses rather than glass as you might do in an optical microscope. That will focus the electrons down into a beam. You can then accelerate the electrons with an electrical voltage so that it's moving at high energy. And finally, with sort of more condensing with the magnets shaping the beam into a fine point, you can also scan that beam across the surface of your sample, again with magnets, in a scan across, so you're covering all areas of the sample sort of one by one in a process called rastering. And then at the very bottom then is your sample, the beam is striking it, and then you have a detector to pick up some sort of signal that's being given off by the sample as it's hit by the electron beam to form your image on the computer. As I said, the whole thing is held under vacuum because the electrons need a vacuum so that they don't sort of interact with gas and get scattered that way. And this is one of the requirements of for a sample that you might want to image in the microscope. First of all, it has to be able to withstand that vacuum. When the beam hits the surface of the sample, there are various processes that can happen. So first of all, obviously, it could pass straight through, you get unscattered electrons, or it could scatter either elastically, which means that no energy is sort of exchanged with the sample, or inelastically, which means that some energy is deposited. But all of those electrons passing through the sample, we're not actually interested in the scanning electron microscope. They're used in a different form of electron microscope called a transmission electron microscope. With a scanning one, we're looking at more of the signals that you can see on the top half of this screen. Primarily, we're looking at secondary electrons. So as the electron beam strikes the sample, it can sort of transmit energy into the sample and electrons can then be emitted from the sample, and these are secondary electrons that can be detected by the detector. And the number of secondary electrons that are generated varies as a function of the angle of incidence of that electron beam coming in. And hence, you can, by scanning the beam across the sample and sort of essentially measuring that angle of incidence from the secondary electron signal, you can build up a picture of the topography or surface of the sample. And that's the main way in which we use the electron microscope to build up an image of what we want to look at. Alternatively, you can look at backscattered electrons, which are elastically scattered. So these are electrons coming into the incident beam and then being scattered back out with the same energy, but in a different direction. And the chance of that happening is related to how many electrons are actually in each atomic shell. So you can use the backscattered electron signal to build up an image of what materials are present in your sample, seeing as different materials will give off different backscattered electron strengths. The electron beam can also displace electrons from the inner shells of the atoms in your sample, and as these inner shells are then filled by outer shell electrons, this can lead to the emission of either X-rays or further what are called O-ray electrons, so you can also detect them. And you can also detect other signals such as shown here, cathodoluminescence, which is where light is given off by the sample as it's struck by the electron beam. What we're really looking at, as I say, in our system is secondary electrons that give you a picture of essentially what the sample looks like, so the surface topology of the sample. Okay. Oh, I should say, because you're striking the sample with an electron beam, if it's not conducting, it will charge up very quickly. And so you need the sample to either be inherently conductive itself, or if you're using want to image something that isn't conductive, you can sputter coat a thin layer of some conductive material, often gold or chromium, so that the surface is essentially unchanged but becomes conducting. And as I said before, the sample also needs to be able to withstand vacuum conditions. Other than that, you can pretty much image what you like. Okay, so that's how the scanning electron microscope works. But now let's talk about the sort of structures that we're making and imaging in it. So here we have a sort of 3D rendering of the sort of structure that we might make, and this one's called a gyroid. So it's a porous material. It's periodic in the 3 directions, sort of the X, Y, Z axes, and the pores are nano-sized, so they're roughly 40 nanometers in size, although you can scale them a little bit. And we can make these in some sort of template material. We use polystyrene, which you can then use to electrodeposit or electroplate some other material that you're interested in. So sort of list here, it could be metals, it could be metal oxides, it could be polymers. But you can electroplate them on your sample around this template. You can then remove the template, and that will give you the nanostructure in the material you want. And finally, you can use that to build some sort of device, whether that's a battery or a solar cell or whatever. But really that begs the question then, well, how do you actually form the template in the first place? How do you get that original nanostructure in polystyrene, which we use to get it in all these other materials? We use a process called, it's a self-assembly process of materials called Diblock copolymers to get that original gyroid structure. This is where you get a polymer made up of 2 different parts, one of which will want to demix from the other. So the easiest way to imagine this is if you think of oil and water. You probably know if you get a glass full of a mixture of oil and water, then pretty quickly the 2 phases will separate, so that you get the water layer on the bottom and the oil layer on top, or vice versa, depending on the density. Well, it's the same sort of idea here. So we have polymers made up of 2 different parts that want to separate from each other. However, because the two polymers are bonded to each other, so each sort of polymer molecule has one part, for example, blue and one part red, which the two will want to separate from each other. They can only do so on a molecular scale because they're bonded. Each molecule is made up of sort of half red, half blue. And so if you deposit a sort of paste of or solution of that material on your sample, heat it up and then cool it back down again to give it some sort of energy, it will try and separate like oil and water, but can only do so on a molecular scale, and this gives you nanostructure. Depending on how much of the one fraction you have compared to the other, so for example how much red you have compared to blue, you can end up with different structures. So you can see here, if you have maybe an equal mix, you might end up with lamellae or strips of two materials alternating through your sample. You can then go to the gyroid phase, which we looked at earlier. Then moving up further, you end up with cylinders standing up from the substrate. And finally, you can end up with spheres of the one material sort of embedded in a matrix of the other material when you get to very low weight fractions. What we're looking at is the gyroid. Now, there are a few reasons why that is the most interesting of these structures, but the main one really is that once we've formed this, this self-assembled phase-separated copolymer, we want to remove one of the materials to end up with that porous template that we had earlier. That you can see in the top left corner. We remove the blue fraction and just get left with the red fraction for the template. So what you need is the structure to be sort of self-supporting, so that when you remove the red fraction, the blue fraction will stay in place with the same shape. And that's only really true of the gyroid structure. The gyroid structure is also bicontinuous, which means that any part on the blue network is connected to any other part on the blue network, and the same for the red sort of network, which is useful for electroconductivity in devices like solar cells or batteries. So it's the gyroid structure that we mostly work with. If I show you a quick video now so you can get a better picture of what that structure looks like. So this is just a sort of computer model of what that structure looks like. You can see there's the two phases there, the blue phase and the red phase. So you can get the one by removing the other once the two have separated from each other in your film. So again. Okay, so that was a sort of computer simulation of what the structure looks like. But now we can actually start looking at electron microscope images of that. You can see here the periodic pattern. So this is the polystyrene template that we initially make. You can see the gyroid structure is formed. And to remind you, the pores there, so sort of the repeat unit that you see repeating again and again is about 40 nanometers in length. And if you then take that template, electrodeposit whatever material you're interested in around it, and remove the template, then you get left with the gyroid structure and the material you're interested in. And what we're looking at here is a sort of cross-section slice through a film of that gyroid. And again, obviously, the pore size is about 40 nanometers. The first practical application that we had for this was in something called an electrochromic display, which is something that changes color when you apply an electric voltage to it or current to it. And these devices had already been developed but had relatively low switching times. So when you applied the voltage, it took a while for the color to change. but because our gyroid structure has such a high surface area, we could make the switching time much quicker, because the charges could get into the metal oxide much quicker, because basically it was all surface. And so what we were able to develop, I'll show you now. You can see here, so that's obviously sort of on an everyday scale, but it's made up of a gyroid structure, nanoscaled material, which we've cast into the shape of that's actually the Cambridge University crest. And you can see as we press the switches to apply a voltage, the color changes really quickly, because essentially the material has two states which you can get between by adding or taking away charge. As I say, the high surface area makes it very easy to bring charges in and out quickly. And so you get very quick changes in color as you push the buttons to get the electrical voltage. Okay, Enrique, are there any questions or?
No, there is no questions up to now.
Okay.
You can continue.
I'll carry on going.
But we are still here, don't worry.
Okay, so that was an example of sort of a technological device that we've made using nanostructure. But as I said, it's not only technology that we're interested in, we also want to do sort of science. And there are other reasons why you might want to look on nanoscale, well, lots of other reasons. But what we're going to look at now is nanoscale in nature. And often nanoscales in nature appear to give what's called structural color. So these are nanostructures that are responsible for very bright colors that you sometimes see in nature. For example, on the wings of this butterfly, which have this very vivid sort of blue. It's also responsible for the colors that you see, for example, in soap bubbles, where you get these sort of rainbow sort of effects in the surface of the bubble. So colors often come from pigments, which are sort of chemical colors. So if you imagine white light coming in from the sun and hitting your object, if seeing as white light is essentially like this mix of different colors, if the object absorbs most of them but scatters one color much more strongly than the others, then it will look to us, when we see the light reflected off of that sample into our eye, that object will look the color that is scattered most. So in this example, we've got a red object that is absorbing all light and scattering red light, so it appears red. That's an example, as I say, of sort of like a chemical color. But in structural color, there's no dye or anything like that absorbing. Instead, it's the structure of the material, again on a nanoscale, so it has to match the sort of wavelength of the light coming in. You can end up with interference giving you reflection of a certain wavelength, so that would be a certain color. If you imagine white light coming in with this mixture of wavelengths, mixture of colors, then if one of them happens to match the distance, for example, here between the layers of your material, then that specific wavelength will be reflected very strongly, and you'll see just that color. So, for example, here you're seeing a red color from the spacing between those layers matching the wavelength of red light. As I showed you before, a good example of this is in a butterfly wing. In the example that I just showed you here, you get a structural color from just a very simple layered pattern, where the layers have a separation that's similar to the wavelength of light. But in nature, often things are slightly more complicated. So you can see these are electron micrograph images now of the butterfly wing. And you can see in the bottom right these sort of Christmas tree structures. The again, the spacing between the sort of branches on the Christmas tree structure is comparable to the wavelength of light, and that's why it reflects these strong structural colors. But the sort of central spine, I guess, of the tree allows the butterfly to have many of these reflectors in place and sort of held structurally onto the wing. So if I show you now a video of imaging the butterfly under an electron microscope. So this is the, I suppose now this is what the screen looks like when you use the electron microscope. Obviously, the sort of main part of it is the image of the actual sample you're looking at, which in this case is the butterfly wing. Already you can see that the wing is made up of these sort of tiles almost. And what we're going to do is zoom in with the electron microscope and see the sort of finer details. Now, if you look on the bottom left corner, it's not so easy to see, but there's a green scale bar, which at the moment shows 100 micrometers. But as we zoom in, that scale bar will change, because obviously the features get bigger and bigger. You can see it's relatively simple, relatively quick to actually take these images. So although this will have been focused previous to taking the film, it doesn't take too long to focus up, and you'll be able to take an image like this within sort of a half an hour or an hour-long session. So we're now zooming in to be able to see the finer structure, what these tiles are actually made of. And you should hopefully be able to start seeing that there are these long sort of spines going down the tile, and in between them you can see struts. And as we zoom in further, you can see that these struts are more or less periodically spaced. And if you look at the scale bar now, that green line is 3 micrometers long. So the distance between those struts is roughly the 500 nanometers of visible light. And as I say, because you get this periodic repetition of layers with a similar sort of wavelength to visible light, that's what enables you to get these strong structural colors. And you can see here just how zoomed in you can get with the electron microscope. So this is going far beyond the resolution that you'd be able to achieve with an optical microscope. You can see the scale bar now has gone to 300 nanometers. And then just a bit of focusing at the end, you can get really quite a nice, clean picture. It's also amazing how sort of intuitive, in a way, it is. I mean, that essentially just looks like a picture of what you're looking at. But it's achieved by scanning that beam, that very small electron beam, across the surface of your sample, sort of in a row.
So this is the biggest that you can see the zoom ring, right? Because it is based on electrons. It depends on the microscope.
Yeah. Okay. So what's the resolution? You mean?
Yes.
The resolution, if you've got all the conditions sort of really perfect, it can go down to sort of a nanometer scale. More commonly, it's sort of on a day-to-day basis. The one that we use here is probably more like 10 nanometers features that you can image. But yeah, that's far beyond what you could achieve with an optical microscope. Unless you use some very sort of fancy techniques with an optical microscope, you're limited, as I say, to the the wavelength of light, which is, going to be sort of 400 nanometers, 500 nanometers smaller.
So this is far very different from an optical microscope. I mean, you use this electronic microscope from the computer, right? So you don't have binoculars just to see how the wing is.
Yeah, so to actually use the microscope, what you're looking at here is just a screenshot of the computer screen that we look at. So obviously, it's taken up mostly by the image itself. Then you're controlling things that are essentially shaping the beam. So that's the magnets that control the shape of the beam to get that really sort of small spot size and focus the beam onto the sample. You can also control the accelerating voltage, so sort of the energy of the beam. So as I said before, the sample can start charging because you're firing an electron beam at it, which is charged itself. So you might need to play around with the accelerating voltage there. So there's a few controls on the screen, but yeah, basically, I mean, as I say, it's pretty simple to use actually.
Yeah, and you have to book to use this kind of microscope because I suppose it is very expensive, so you don't have a lot of them, right?
Yeah, so we have one of these microscopes at the Nanoscience Centre. Across the university in total, I would guess there's probably something like 10 to 20. So yeah, you need to book, but we take it in turns to use it. But with this one, fortunately, as I say, it doesn't take too long to set up and use. So within a half hour or an hour even, you can get reasonable images.
Okay, thank you. You can continue.
Cool. Okay, so as well as just imaging things that we take from nature, so for example, getting a butterfly wing, putting it under a microscope and seeing what there is, we can also try and learn more about the system by trying to replicate it ourselves. And so at the top of the screen here is the actual butterfly wing. I should say a different one to the one that we just saw in the video. But again, with this sort of Christmas tree structure. We tried to replicate that here. So we built pillars made up of layers of materials, alternating materials, and then tried to chemically etch out one of the materials, leaving behind the other one to get that sort of branch structure. And by doing it, sort of carefully controlling the amount of time that you do the etching for, we're hoping to leave behind the core tree part in the middle. And you can see at the bottom then is our attempt at replicating the butterfly wing. So it's not perfect, but it's kind of looking similar, and you can see structural color from this. So as I say, you can, by trying to replicate what you see in nature, you can learn more about how it works, maybe how it forms, and you can also end up developing new technologies, borrowing tricks from nature, which is called biomimetics. So it could be, for example, trying to copy structural colors that we see in nature. Also, people have been working on trying to copy the nanostructures you find on gecko feet, which they use to adhere to a wall and sort of climb up vertical surfaces.
Okay, so I thought everything was pigment colors. I did not know about the structural colors. So you are trying to replicate what you have learned from nature, and does it have any commercial application?
Yeah, so like I said, I'm not sure if anything maybe has been commercialized yet, but certainly people are working on sort of ideas that could be. So that's what I was saying, structural colors and maybe would be something, and also people are certainly working on trying to get adhesives that are based on the sort of structures you find on gecko feet.
And what material did you use for the replica?
So this wasn't actually my work. So I don't know the exact materials. Yeah, I don't know, I'm afraid.
Okay, thank you.
Okay, so if I show you now another video that we took under the electron microscope, this time of a fly's eye. Which hopefully will load. Okay. So this is what it looks like. This is now just a starting with a sort of video camera of inside the electron microscope. So you can see the electron gun is that sort of cone at the top of the screen, and then underneath, sitting on what we call stubs, are the samples we're looking at, and that's on the base that you can rotate to move around the sample. And the fly that we're looking at is what's been stuck down on top of the stub underneath the electron gun. So you can switch. So if you move the sample then up towards the gun to start imaging, and then we switch to looking at the sample itself. So you can see this time we've started off looking at very high zoom. We're going to zoom out of the fly's eye. So again, if you look at the scale bar, you can see it's 200 nanometers. And that, as we zoom out, that will slowly decrease. And what you start to see is that the fly's eye is made up of these sort of collection of circular objects. So you can easily, with the SEM, measure distances, as shown here. So you can see that it's about 25 micrometers across. And obviously the structure is roughly sort of circular. As we zoom out further, you can see more and more of these circular objects. So in fact, that's because the fly's eye uses a compound eye technique, rather unlike ours. So it basically detects the direction that light is coming into its eye by channeling it down one of these array of sort of tubes, essentially. I'm not a biologist, but tubes that collect the light. And obviously, if you can tell which direction the light is coming from, then you can use that to build up the image. So that's how the fly's eye works.
Do you know anything about gecko nanostructure? Because there is some question in the chat about if it is used to Windows washing robots. Do you know the gecko nanostructure?
Sorry, it's used for what?
For Windows washing robots. The gecko is this kind of lizard that can be in the window without falling. So this kind of nanostructure, that can be another possibility to take things from the nano world to the real world and commercial applications.
Yeah,
they are telling about that in the chat.
Yeah, so that's as I say, that's an example of taking something that we found in nature and trying to then use it to make our own. So yeah, the gecko feet have like a hierarchical structure. So it's kind of a structure that repeats itself on different length scales and has these kind of fibers that get smaller and smaller and smaller, eventually going down to the nanoscale. And these are made of, I think, strong materials which become soft at such scales, and so they can use that to adhere to the wall very strongly, but also be able to peel it off quite easily, and that enables them to walk across the surface.
Okay, thank you.
For colour in a butterfly wing, which is sort of like obviously a living example from nature. You can also find it in sort of inanimate objects, also in nature. So here we're looking at an opal gemstone on the left, and you can see the structural colour again, this bright colour. So this is formed as silica, which is sort of sand, basically, particles that are roughly spherical with the same sort of diameter, and again on a nanoscale. So it's always coming back to this idea of things being periodic on a nanoscale that matches the wavelength of light. So these particles of sand can, in the right conditions, slowly pack themselves into a periodic structure similar to the one that I've shown in the bottom right. So it's like these closely packed stacking of spheres. And because you get these sort of repeating layers again with nanoscale separation, that's how you end up with the structural color. So that's an opal gemstone, but we've tried to replicate that here in the lab. So rather than using sand, we're using polystyrene, and our polystyrene spheres have very well controlled spherical shape and all the same diameter. And if we suspend them in a water solution, which you can see in the sort of test tube on the right, and then slowly drag that solution across a substrate so that you get evaporation just from one end, then as the water evaporates, it pulls the polystyrene spheres towards the evaporation edge, and they will try and pack into the densest packing they can, which is that opal structure. And if you do that, wiping the blade across the surface carefully, then you can deposit an opal structure across your substrate. So I'll show you now first a video of us depositing the opal under an optical microscope. So you can see here, these are the polystyrene spheres that are packing into the opal structure. And we're slowly dragging that sort of collecting edge across. So that's where the water is evaporating. And you can see the spheres, the polystyrene spheres, self-assemble into that opal structure just by trying to adopt the densest packing that they can. I'll play it again. I should say, so this is actually using slightly bigger polystyrene spheres than we normally do. We've cheated here so that you can see it under the optical microscope. Because with an electron microscope, it has to be under vacuum, so you couldn't image this under the electron microscope because you need the water to be in liquid form. But it's exactly the same process that we use with the same sort of polystyrene spheres, but with a much smaller diameter. And you can use the same process to get nanoscale opals as well. If I show you now, this is looking then at an opal that we formed with nanoscale polystyrene spheres, and we're looking at it once it's already formed under the electron microscope. So again, this is just moving the sample into place underneath the electron gun. And then switching to the electron microscope image. And again, we started out very zoomed out here. So you can see the scale bar is 200 microns. And then we're going to zoom in to see the structure. You should hopefully start to be able to see these sort of striped patterns appearing, and that's because of the that sort of interference almost from the periodic array of the polystyrene spheres. But we're still at a very sort of zoomed out scale. So as we zoom in further, you should be able to see the individual spheres. So if I pause here, you should be able to see now, you can see that that's actually made up of this densely packed array of polystyrene spheres. They are mostly arranged very nicely in the opal structure. You can see certain sort of gaps where there's a sphere missing. That's quite common in both in these opals, but also just in general with any crystalline structure. You often find these sort of defects. And then also you can see on the sort of going down the left part of the screen, there's this sort of jagged line where the pattern kind of changes direction almost. And that's an example again of another feature common to all crystalline structures. It's sort of like a domain boundary where you get different alignments of the pattern on either side of that line. So they're kind of, both of those defects will be, well, obviously, imperfections in the opal structure. But generally, you know, you get fairly nicely arranged structures. So if we zoom in further, we can see the individual spheres more clearly. And you can see now we're able to really zoom in and see very nicely those spheres. And actually, I should say that the resolution there is limited by our screen sort of grabbing software. So the actual image that we would see on the microscope is even clearer than that. And these are spheres that are, I think they were 500 nanometers in diameter, although you could image easily beneath that. Okay, so this is the sort of resolution that we can see on our screen now. Again, sort of just stills taken of the opal structure. So you can use polystyrene spheres that are all the same size, which is what I was showing you just now, as you see on the left. We can also, by carefully balancing the fraction of one side to the other, you can still get opal structures but with a mixture of sphere sizes, and get sort of these binary mixtures still forming periodic patterns. Again, the idea of templated fabrication can be sort of repeated. So before we're using a polystyrene gyroid as our template to electrode plate metals or metal oxides or polymers around, and then remove the template to get our structure. Well, these are polystyrene spheres, so you can do exactly the same thing, but using the opal pattern instead, and then you get left with not the opal pattern, but the inverse of that. So that's what's shown on the right here. If you use a single sphere size, then you'd get these kind of hollows around where the spheres used to be. And with the binary patterns, you get these craters with diameters of different sizes. And again, this can be applied to any technology where you want to have really high surface areas compared to volume. So coming back to sort of similar technologies, solar cells, batteries, photonic crystals, which are essentially a fancy way of using structural color. And then also, just at the end, an opal a dress that was made using opals to give structural color was also used in a fashion show once. If I could show you now a video of an opal that's been made with polymers so that it's stretchable. And you can see the structural color from that. So that's in this video here. You can see as you stretch the polymer opals, what you're doing is changing the spacing between each sort of opal sphere, and that changes the color that the material has. So stretching it, you can change the color, and it's reversible. So as you unstretch it, it goes back to its original color. Okay. So I think that's the end of the presentations I had ready for you. Hopefully you've seen a bit now of what we use the electron microscope for, the sort of images that it's able to take and the scales that it's able to go down to, and hopefully also some of both the technologies that we are trying to develop using nano sort of scale applications, and also some of the features that we see in nature that we can learn more about and also maybe potentially use as well.
Okay, thank you very much, Harry. Just about your PhD, are you finishing it, or how long do you expect it to finish?
So I've just finished the second year of my PhD.
Yeah.
PhDs normally take between 3 or 4 years, so I guess another year or two probably. I'll have to wait and see. If things go well, a year.
Yeah, you still have to disseminate your results, right?
Yeah, yes, that's true.
Okay, thank you.
No problem. Are there any questions, or?
If there is another question, people are saying in the chat that it was really amazing and they love it. So they were there. They were following your explanations, but I think everything was really, really clear. For the people, just to see that this is an example how you can communicate and collaborate with a scientist, with a real scientist, and a virtual visit and see how they work, what do they do for a daily living, what do they investigate, because these themes, these topics are not explained in a daily basis in the curriculum. So they are very interesting and they can motivate your students. So if you have any questions now, or even maybe in the forum, because there is a forum in the MOOC in the module 5, and also the recording, because we have been recording, so if you have lost any part, or for people that could not come, so everything will be here in the resources section. So I think there is no question. People are saying thank you very much. It was really interesting and so on. So thank you, Harry. I think we can finish here.
Okay, great. No problem. Well, thank you very much. It's good to know that people are enjoying it.
Have a good luck with your dissertations and with your publications for the PhD.
Yes, thank you.
Good luck. Bye. Thank you.
Thanks.
Thank you, everybody.
Bye.
Bye.